In Module 8, we'll begin to cover the fundamentals and applications of an area of chemistry called electrochemistry, which can basically be thought of as electron transfer reactions. Now, chemical reactions where the principal driving force originates from an electron transfer from one ion or molecule to another are called oxidation-reduction reactions, many times called redox reactions for short. Oxidation is defined as the loss of electrons. Reduction is defined as a gain of electrons. A classic example of a spontaneous redox reaction is the oxidation of zinc metal by copper 2+ ions in a solution of copper sulfate with the simultaneous reduction of copper 2+ ions by the zinc metal. Now that may not make a lot of sense until we show you a reaction written out and some pictures. So the balanced equation for this reaction would be zinc metal plus aqueous copper sulfate going to aqueous zinc sulfate plus copper metal. If we look at the reactants, at first what we have here is a blue solution in a beaker, which is the copper sulfate solution, into which we simply place a zinc piece of zinc metal. So we've got that labeled here. And as soon as we do that, we start to get a reaction. And over time, you get the products of the reaction, which are copper metal and zinc sulfate in solution. Now, the two obvious things that have happened here in this reaction are that the zinc metal, which was metallic colored, silver colored metal, seems to have turned black and crusty, and the copper sulfate solution seems to be a lot lighter than it was before the reaction started. The reason the solution's a lot lighter is that copper 2+ ions are what give the solution a blue color. The copper 2+ ions are being deposited on the zinc electrode as copper metal, so they're leaving the solution, so the solution becomes lighter blue. Eventually it would go colorless because zinc sulfate, when dissolved in water, has no color. You might wonder why the copper metal that's produced here isn't copper colored. That has something to do with the texture and structure of that solid. It's been reported that finely divided copper can actually appear black rather than copper colored. So we could ask, why is this a redox reaction or an electron transfer reaction? Well, let's look at what's going on. We started out on the left in the reactants with neutral zinc metal atom, and on the right, after the products are formed, the zinc has a 2+ charge. It's a zinc ion in solution. So each zinc metal ion has lost 2 electrons to form zinc 2+ ions. So in other words, the zinc metal is oxidized, and the copper 2+ ions that used to be giving this solution the blue color have been reduced to copper metal atoms. Each copper 2+ ion has gained 2 electrons to form copper metal. It would actually be helpful to write out the net ionic equation for this reaction of zinc metal with copper sulfate solution. So to do that, we'll write the original equation and then expand the equation to show more information. And by that we mean that copper sulfate aqueous really means copper 2+ ions plus sulfate ions separated in the solution. And on the right, zinc sulfate aqueous really means zinc 2+ ions and sulfate ions separated in solution. This is where remembering what the ions are in that ion list that's available for reference during the quizzes would be helpful. In other words, you should be able to recognize that copper sulfate consists of copper 2+ ions and sulfate ions. That's a throwback to General Chemistry 1, where you learned how to name ionic compounds. In any event, you'll notice that sulfate ion is common to both sides of the arrow. So we're going to cross that out, call it a spectator, and then write the net ionic equation, which would be zinc metal reacting with copper 2+ ions to form zinc 2+ ions plus copper metal, and we can identify that it's the zinc that was oxidized. Each zinc loses 2 electrons to form zinc 2+ ions, and it's the copper ions that were reduced or underwent reduction. Each copper ion gained 2 electrons to form copper metal. So this is a redox reaction because there's an obvious electron transfer reaction going on. One thing you should notice is that electrons are what we call conserved in a balanced redox reaction. And what this means is that the number of electrons lost, which was 2 in this particular case, has to equal the number gained, which was again 2 in this particular case. So the number of electrons lost by one species in solution has to equal the number gained by another species in solution or in the reaction. Let's look at some terminology to make sure that we're all on the same page here. In this reaction, the element zinc has been oxidized to the zinc 2+ ion by loss of 2 electrons. Each zinc atom has undergone oxidation to lose 2 electrons to form a zinc 2+ ion. The ion copper 2+ has been reduced to the element copper by the gain of 2 electrons. We say that the ion copper 2+ acts as the oxidizing agent. It accepted 2 electrons from zinc. This can sometimes be a little confusing because we say copper 2+ has been reduced, and then we say it's the oxidizing agent. What we mean here is that copper 2+ acted as an agent of oxidation to remove 2 electrons from zinc. So copper 2+ is itself reduced, but it's reduced by acting as an agent of oxidation of the zinc. So it's an oxidizing agent. It caused something else to lose electrons. And the element zinc acts as a reducing agent. So zinc itself loses 2 electrons and is oxidized, but in doing so, it gives 2 electrons to the zinc. So it acts as an agent of reduction to the to the copper 2+. So the zinc acts as an agent of reduction, giving 2 electrons to copper 2+, which is reduced. If it just sounded like I was talking in circles, I was not. These are terms you need to be familiar with. Now, it was fairly obvious that this example reaction was a redox reaction, meaning we could see that electrons were transferred from the zinc to the copper. Well, sometimes a redox reaction, something that's an electron transfer reaction, is not so obvious. So for example, here's a more complicated net ionic equation for a redox reaction. And here you might say, well, there are negative and positive ions, there's some neutrals in here. There's probably a high probability that there's some sort of transfer of electrons. But A, how do you know that? And B, how do you know what in this solution is accepting electrons and what in this solution is donating electrons? Well, the way we can identify in a redox reaction what's being oxidized, what's being reduced, what's acting as the oxidizing agent, what's acting as the reducing agent, is by assigning to each atom in each ion or molecule something called an oxidation number. Well, we probably need to review the assignment of oxidation numbers. Many times this is covered in first semester general chemistry, but it warrants a review here. If you've never seen this before, well, the time is now to look at how we do this. I'm just putting up this table here, and you can see that this is going to become tiresome working through these rules. The only way to do it is to just do it. So let's get going. On the left, we have the guidelines, and on the right, we'll do some examples. So the first guideline is the oxidation number is 0 for any atom in its elemental form. Well, what are some examples? The oxidation number for each fluorine atom in F2, which is the elemental form of fluorine, is 0. So each fluorine in fluorine gas, F2, which is the elemental form of fluorine, is 0. The oxidation number of each of the zinc atoms in the zinc metal in our first redox reaction. Zinc metal is zinc in its elemental form, so the zinc atoms have an oxidation number of 0. The oxidation number for a monatomic one-atomed ion is equal to the charge on that ion. This is easy to remember. One thing you need to recall is what a monatomic ion is. It's an ion that's made up of one atom. So sulfide ion, even though it has a 2- charge, is a monatomic ion. It's a one-atomed ion. So we say the oxidation number of the sulfide ion is -2. The oxidation number of the copper 2+ ion is +2. This guideline seems almost self-evident, but it's important to remember. The oxidation number of oxygen in either ionic or molecular compounds is always -2. The only exception is for the peroxide ion, which is 2 oxygens bound together in the entire group, 2 oxygens with a 2- charge, where each oxygen atom has an oxidation number of -1. Examples: the oxidation number of oxygen in water is -2. The oxidation number of each oxygen in the ionic compound copper sulfate is -2. The oxidation number of each oxygen in sodium peroxide, which consists of 2 sodium+ ions and 1 peroxide ion, is -1, because the peroxide is the only exception to the -2 rule for oxygen atoms. The oxidation number of hydrogen in molecular compounds is always +1. Now, when combined with a metal in an ionic compound, now you won't see this often, but it's worth pointing out, hydrogen is in the form of what's called a hydride ion, and so has a -1 oxidation number. For 99% of the cases, you will see hydrogen has a +1 oxidation number, except of course if it's an elemental form. The oxidation number of each hydrogen in H2O is +1. The oxidation number of each hydrogen in phosphoric acid is +1. The oxidation number of hydrogen in what's called sodium hydride, which is one of these different situations, is -1. The oxidation number of fluorine in ionic and molecular compounds is always -1. So examples: the oxidation number of each fluorine in the ionic compound MgF2 is -1. The oxidation number of each fluorine in the molecule difluoromethane is -1. Now you say, wait a minute, up here we said the oxidation number of fluorine is 0. Well, remember, that was just for the general rule that the oxidation number of anything in its elemental form is 0. Here, fluorine was in the elemental form, so of course its oxidation number is 0. If it's not in the elemental form F2, the oxidation number of fluorine will be -1. In a neutral compound, the sum of the oxidation numbers of the atoms of all the elements in the compound, taking into account the number of each type of atom, is 0. By this time in the table, you're probably getting tired, but this is an important guideline. Look at the example. In the compound copper sulfate, the oxidation numbers are as follows. Now, copper sulfate has one copper 2 plus ion, and that of course would have a +2 oxidation number. It has one sulfur atom with a +6 oxidation number, and it has 4 oxygen atoms, each one with a -2 oxidation number, and there's 4 of them, so that gives -8. So we get +2 from the copper 2 plus, +6 from the sulfur, -8 from the oxygen. So the math here is +2 plus a +6 plus -8 equals 0. So the oxidation numbers of all the atoms in this compound equals 0, taking into account the number of atoms of each. One of the things you might ask here is, where in the world did I get the oxidation number of sulfur being +6? Well, I think we'll demonstrate this in the next guideline, but what I can tell you now is that we know copper 2 plus was +2 because of an earlier guideline. We know that each oxygen was -2 because of an earlier guideline. And if all the oxidation numbers have to add up to 0, then we know sulfur would have to be a +6 to get the math to work out correctly. Let's go on to the final guideline here. In a polyatomic ion, the sum of the oxidation number of the atoms of all the elements in the ion, taking into account the number of each type of atom, equals the overall charge on the polyatomic ion. So let's look at the sulfate ion, which is of course in copper sulfate. We have 4 oxygen atoms, which we know are -2 each, so that's -8. We know that all of the oxidation numbers in this polyatomic ion have to add up to -2, which is the overall charge on the ion. So that leaves only a +6 for the sulfur. Well, you'll notice here that pretty much besides the last two, which are important rules, we seem to have zeroed in on 3 elements: oxygen, hydrogen, and fluorine, and we haven't said much about the typical oxidation numbers of all the other elements. It turns out that if you can nail down the oxidation number of oxygen, hydrogen, or fluorine in many compounds, you can, and take into account some of the other guidelines, it's easy to figure out what the oxidation numbers are for some of the other atoms not listed in the guidelines. We'll do some examples. The first thing we'll do is apply these guidelines to the zinc copper sulfate reaction that we just covered. And I'm going to put this in the middle of the slide here and make it a little bigger, because we're going to assign oxidation numbers to each of the atoms here and try to go back and name the guideline that gives us the ability to assign the oxidation number. And recall that I'm going to assign oxidation numbers on a per atom basis, and you'll see what I mean in a minute. The oxidation number of zinc solid here is 0 because zinc is in its elemental forms, and the oxidation number is 0 for any atom in its elemental form. Well, how about copper sulfate? Well, remember, in a neutral compound, which is what copper sulfate is, the sum of the oxidation numbers of the atoms of all the elements in the compound, taking into account the number of each type of atom, is 0. Well, what is copper sulfate made up of? It's made up of 1 copper 2 plus ion and 1 sulfate ion. We know the oxidation number of the monatomic copper 2 plus ion is +2 by one of the guidelines. So we'll put that right here. The oxidation number of each oxygen is -2 because it's not a peroxide. So if we want to decide what the oxidation number of sulfur is, we could say that X is the oxidation number of sulfur. We know it's +6, but this is how you'd go about finding it. The copper 2+ is 2+ X, which is the sulfur oxidation number, plus 4 times a -2 for the oxygens has to add up to 0, so X has to equal +6, so we put that right here for the sulfur. And again, notice I'm assigning oxidation numbers on a per atom basis. So I know there's 4 oxygens, each at -2, but I'm listing the oxidation number for each individual oxygen. Let's go over and look at zinc sulfate. Well, zinc sulfate's a neutral compound, so the sum of the oxidation numbers of the atoms of all the elements in this compound, taking into account the number of each type of atom, is 0. We know that zinc sulfate is made up of one zinc 2+ ion and one sulfate ion, and we know the oxidation number of monatomic zinc 2+ is +2. So I'll put it right here. The oxidation number of each oxygen atom is -2. So we'll put it right there. And this leaves assignment of the sulfur, which is done in exactly the same way as in copper sulfate. So we give that a +6. And finally, the oxidation number of copper is 0 because the oxidation number is 0 for any atom in its elemental form. Well, after assigning oxidation numbers, we can identify this as a redox reaction because there is a change in oxidation numbers going from reactants to products. Zinc started out with an oxidation number of 0 on the left, and on the right it has an oxidation number of +2. Copper, on the other hand, started out with an oxidation number of +2. It's now 0 on the other side of the arrow. So therefore, this is a redox reaction. Not all the atoms have to change oxidation numbers. Sulfur and oxygen do not change oxidation numbers. So the oxidation number of zinc goes from 0 to +2, so it's oxidized. The oxidation number of copper goes from +2 to 0, so it's reduced, it gained electrons. And the oxidation numbers of sulfur and oxygen atoms are unchanged. The oxidizing agent is copper 2+ because it causes zinc to lose 2 electrons. The reducing agent is zinc metal because it caused the copper 2+ to gain 2 electrons. Let's do a second example. This is this more complicated example that we brought up as an example of a reaction that might be a challenge to identify what's oxidized and what's reduced, and we'll go through assignment of oxidation numbers here. Well, the oxidation number of hydrogen ions are +1 because the oxidation number of a monatomic ion is equal to the charge on that ion. Let's look at the dichromate ion. Well, we know to start with that oxygen here is going to have to be -2. And we are also reminded that the oxidation numbers of all the atoms in this dichromate ion, taking into account how many there are of each atom, will have to add up to -2, the charge on the ion. If you do the math here, if you have 7 oxygens times -2, and then you add in 2 chromium atoms for which you do not know the oxidation number, 2x, that math expression has to add up to -2, so the oxidation number of chromium there has to be +6. The oxidation number of chloride is, of course, -1, and the oxidation number of chromium, 3+, is, of course, +3. If we get to water, we know oxygen has a -2 oxidation number, and we know hydrogen has a +1 oxidation number, and that all makes sense because this is a neutral compound, So all the oxidation numbers, taking into account the number of atoms of each element, have to add up to 0. 2 times a plus 1 minus 2 will add up to 0. And finally, this is chlorine in its elemental form, so the oxidation number would be 0. Well, after assigning the oxidation numbers, we can definitely say this is a redox reaction because there is a change in oxidation numbers going from reactants to products. The oxidation number of each chlorine goes from -1 on the left to 0 on the right. Therefore, it's losing negative charges or losing electrons. So chloride is being oxidized to chlorine. The oxidation number of each chromium is +6 on the left, and on the right it's +3. Therefore, it must have gained negative charges. So it's being reduced. The oxidation numbers of hydrogen and oxygen in this particular redox reaction remained unchanged. The oxidizing agent is dichromate. Actually, it's the chromium +6 ion in the dichromate, and the reducing agent here would be the chloride ion. Chloride's losing electrons to the chromium, so chloride's the one that is reducing the chromium. Let's do another example. How about this reaction? 2 silver ions being introduced into a solution of cobalt bromide to produce silver bromide precipitate plus cobalt 2 ions. Let's assign oxidation numbers. Well, silver ion would be +1. In cobalt bromide, remember all the oxidation numbers have to add up to 0. Cobalt 2 plus and 2 bromide ions are what make this up. We know the oxidation number of cobalt 2 plus is +2, which would mean the oxidation number for each bromide would be -1. We also know that bromide's -1 because bromide is a monatomic ion. And so we can assign those oxidation numbers. Going over to the other side, we have silver bromide, which consists of a silver ion +1 and a bromide ion -1. So we can assign those. And finally, the oxidation number of cobalt 2 plus, of course, would be 2 plus because the oxidation number is equal to the charge on a monatomic ion. Well, let's examine this reaction. After assigning oxidation numbers, we realize that this is not a redox reaction because going from reactants to products, there is no change in oxidation number for any of the atoms. Silver is +1 on the left, it's +1 on the right. Cobalt's +2 on the left and +2 on the right. Bromide is -1 on the left, -1 on the right. And so this is actually just a precipitation reaction with no electron transfer involved. And let's try a fourth example. This is the combustion of butane gas. Combustion would be reaction with oxygen. This is the balanced equation. Let's take a look at the assignment of oxidation numbers here. Well, in butane we have carbon and we have hydrogen. We know that the oxidation numbers all have to add up to 0 because this is a neutral compound. We can go right to hydrogen to assign that first because the guidelines say the oxidation number of hydrogen in molecular compounds is always +1. Now we have that as an anchor and we can figure out the oxidation number of carbon. So let's do that. We'll let X equals the oxidation number of carbon. So that means we have 4 times X, X being the unknown oxidation number of carbon, plus 10 times a +1 from the hydrogens, have to add up to 0. If we solve for X, we get an oxidation number of -2.5. Now don't let this freak you out. You can occasionally see fractional oxidation numbers. We'll come back and mention how we can make more sense out of that in just a second. The oxidation number of oxygen in elemental oxygen O2 is 0. Let's look at carbon dioxide. This is a compound where the oxidation numbers should all add up to 0. We know that oxygen's always -2, which leaves the only choice for carbon as being +4. And if we look at water, we've done this before, oxygen's -2, hydrogen's +1. So let's examine this reaction. We can see that this is a redox reaction because there's a change in oxidation numbers going from reactants to products. Well, what are those changes? Well, each carbon on the left was -2.5 oxidation number, and each carbon on the right is +4. So carbon has obviously been oxidized. It's lost negative charges. Oxygen was 0 on the left, and it's -2 on the right in two different places. So oxygen's undergone reduction. And so we have a redox reaction. Now the oxidizing agent in this case would be oxygen, because oxygen is gaining electrons, so it's removing them from the carbon. So it's causing the carbon to be oxidized. So oxygen is the oxidizing agent. What a coincidence. The reducing agent would be butane, but specifically the carbon in the butane, because carbon is losing electrons. To get a positive oxidation number, those electrons must be going to the oxygen. So carbon is reducing oxygen to the oxide ion in each of these compounds. Let's talk about this fractional oxidation number here for a minute. Despite the fractional oxidation number for the carbon atom, we do need electrons to stay whole. So let's count the total number of electrons lost and gained in this balanced redox reaction. The total number of electrons lost would be 8 carbon atoms undergoing a change from an oxidation number of -2.5 to +4. So again, each oxygen goes from -2.5 to +4. That's a change of 6.5 oxidation number units, and there's 8 carbons altogether undergoing this change, and 8 times 6.5 is 52. So this balanced equation is showing the transfer of 52 electrons from the carbon of butane to the oxygens. And the oxygens would be gaining 2 electrons each, and we have 26 of them, and 26 times 2 is 52. So the oxygens have gained 52 electrons from the butanes that lost 52 electrons, or the carbon in each butane. So in the end, we do have whole numbers of electrons being transferred. And the total number of electrons lost equals the total gain, which should be true in a balanced redox reaction. In the next lecture, we're going to review how we might actually balance a redox reaction. So we won't just be given balanced redox reactions, we'll talk about how to balance them.